I want to thank also Alexei and Olga for making it possible for me to be here. I normally haven't been traveling as widely in Europe in the last few years, so to be in Russia, especially in Moscow, is a delightful. I was here 30 years ago, which is before most of you were born, but in any case, it's quite different and lovely here. All right, I'm going to be talking about automatic visualization, and then as I indicate or outline this research program, I will then move on to show you how visualization can profoundly affect the way you compute models, whether you're a CAGLer or whether you're someone who needs to provide results for a bank, which is highly regulated, and therefore you have to be concerned with an interpretation of results. So the first thing I want to do is present to you the evolution of this idea of automatic visualization, because it's a little bit more than simply making graphs for variables because you press a button. It's far beyond that. So the earliest work I did on this problem was jointly with Graham Wills. How this works: we have a data source. In this case, I'll just grab some data on baseball players. These, we'll see what those are. I'm just going to drag them in there. And the program figured out, looking at the data set, what the variables were, what the interesting patterns were in the data set itself. On the top, you see a network diagram that the program constructed from associations between the variables. So continuous variables, that would be Pearson correlations, for example. And those are kernel densities on the left of significant variables, and on the bottom are hexagon plots, hex binning plots of pairs of variables that the program considers interesting. Now, what's unusual about this is we just took a data file with strings and continuous, numeric variables, but let's grab a copy of Moby Dick. That's on the Gutenberg website. That's Melville's famous long novel. Not quite as long as War and Peace, I don't think, but... And you notice it did a network analysis based on n-grams. So how did it know how to do that? It's like a joke that some people tell. It's a third-grade joke. I'm sorry, I apologize. But a little boy runs over to his mother and says, "How does this work? It's a thermos?" And she said, "Yes, what's the problem?" And he said, "Well, you put hot water in it, and it stays hot. And you put cold water in it, and it stays cold." And the mother says, "Yes, and the problem would be?" He said, "How does it know?" Well, that's kind of like this program. Let me show you another instance. I'm going to grab a painting by Jackson Pollock and drag it in there, and the program knew, because it's a graphics file, how to do a breakdown of the hue, saturation, and brightness of the file, and do a plot. And you notice in Pollock's painting, there's a very small range of hues and saturation. Well, okay, we could actually grab some random data, bring that in, and nothing happens. There's no network diagram. Why is that? Well, the program uses something called the false discovery rate of Benyamini and Hochberg. If you're a statistician, you know all about that. People in machine learning don't generally know as much about statistics. But the point is, this protects you from making false inferences. So that's another principle I wanted to illustrate. Why don't I just take the whole jar file of AutoVis? There's the Java archive file it's been laid out as a graph layout. So in effect, this whole program, and I haven't got time to show you other things it looks at, it was inspired by the idea, how can you look at a data set and analyze the data set without telling the data set about a model? Is it supervised or unsupervised? No, we don't care. What can we get from that particular way of looking at things? Now, a second thing, and let's see if this happened. Oh, yes. Oh, we got our little... Should I try to drag that off, I guess? I don't know why it's occluding. There, okay. So, the second thing, which I can't show you actually, is called a second opinion. About 5 years after we worked on AutoVis, I thought, why don't I try to write an entire statistics package, but give it a completely different way of working from older packages. I had written a package called Systat in the 1980s that was kind of like SPSS or Stata or other programs where you had menus. And I thought, can I distill all of statistics into 7 words? That's biblical. But put them into 7 words like predict, summarize, classify, and have a very simple interface. If you look up there, they're little sentences. They're like data flows. You get data, you analyze the data, you pick a way of analyzing the data, and then it presents to you in sequence. It's sort of like a wizard, but I hate wizards because they're so complicated. This one just presents to you the next step, and then you may backtrack at any time. So if I had 10 analyses under that word analyze, I could go to any of those words and open it with a drop-down like that, just clicking on it. And then right below there is the output. The other thing I wanted to do was statistics packages, and machine learning packages for that matter, spit out tons of data, of results. A statistician I know from years ago said, the great thing about SAS is you put in, SAS is a very big statistics package. You put in a few numbers and you get out tons of numbers. Or like when I remembered in the computer center when people carried paper out and they'd run SPSS and they'd proudly walk out the door with a stack of printouts this thick. Well, that's not the way to do statistics or analytics or data science. What I think is what you see below. I devised an HTML document output with live graphs. So that thing you see at the bottom is a scatterplot matrix, which shows you all the variables you put into, in this case, the cluster analysis. And you can look at the patterns. It's colored 3 colors according to the clusters that the program found. Now, I assume all of you have run k-means in one form or another, right? I should ask anyone, raise your hand if you've never run k-means. The fact is, and I'll put this strongly, and I'm just generalizing here, none of the k-means programs are programmed correctly. By that I mean Python, I don't care, Amazon, Google. K-means, this program finds the right number of clusters for the data set. That's not as simple as just randomly generating some points and then asking to cluster them. It's much deeper than that, and I'm surprised that most people who have done applications involving k-means didn't understand that. If they'd gone back and read the history of k-means, they'd know how to do it correctly so that the data set actually comes up for iris with the 3 clusters. If you go to Wikipedia, by the way, it will say you can't use the iris data set to test clustering programs because it has 2 clusters when you run these programs. And that's because the writer of that particular Wikipedia paragraph didn't understand that there's subtleties to the k-means algorithm. Well, enough of this salesmanship. Let me move on to the last column. This is the most recent incarnation of what I and the team have been trying to do at H2O. The previous two packages were in memory. They were written in Java. They can handle moderate-sized data sets, 100,000 rows and maybe 100 columns. What happens when you get a data set with 1 billion rows? How do you visualize that data set? Even just a scatter plot. You certainly can't do it by plotting all 1 billion rows. You'll get a big black spot in the middle of the screen. So obviously you need to turn to aggregation. Now, Facebook and some companies have aggregated to do these kinds of two-dimensional plots. Facebook did it on the surface of a sphere, which is mathematically two-dimensional. And that's not hard. You just aggregate over each pixel located on the surface of the, and then plot the pixels. But it's more complicated when you have high-dimensional data. So suppose I have 50 variables, and I want to compute principal components and display them in a singular value decomposition on 50 variables on 1 billion records. Well, again, you cannot compute on the raw data. If you compute the scores on the rows, that is the row eigenvectors, you'll have too many points. You can't pass them over the wire to a browser, and you also would get a big black spot. By the way, conventional visualization systems today, like D3, Vega Light, and so on, can only plot about up to maybe 5,000 points before they slow down. So those are the restrictions that we struggled with. And I'll just hope this works. Bring up my browser and log on to AWS, where I have at the moment, we're hooking into H2O's AutoViz. There it is, good. Now some of these files are not as big as I mentioned, but they're big enough to give you an idea. Let me, for example, grab one here, the credit card data set from UC Irvine, Kaggle, whatever. And all I'm going to do is press it and get a little drop-down menu, detail, split, predict, visualize, delete. Let's just say visualize. And what the program's doing is the way AutoViz in the old version did, looking for interesting patterns. For example, on the far left, on the top, it says skewed histograms. So we click on that little thumbnail, and now we can look at all the skewed histograms in the data set. What do we do with those skewed histograms? Well, that's the topic of the rest of my talk. But the point is, the program was able to find that by computing a very robust measure of statistical skewness. I don't cube values to get skewness. There are other algorithms that work better. And similarly, here's the association diagram I told you about that Graham and I did inside the original AutoViz, and we can clip those edges and filter it, and any two variables that are connected by an edge are more closely related than variables that are not. So I won't spend much more time on this, except to say, yeah, it also gives you heat maps which have been sorted to reveal relationships and things like parallel coordinates, which some of you may be aware of in visualization, and so on. So now I'm going to log off here and move on. oops, I signed in again, sorry. Log off and go back to the presentation to spend the rest of the talk on how you, I did want to do a, good. Now, there's that, it should disappear. Let's see what happens. All right, now, unfortunately, that's not appearing on my screen here. Was it? Oh, thank you. Now I'm going to stay with this and not try all this switching around anymore. Here's what I want to talk about. Because people who have used AutoViz say, well, what do I do with it? I just see all those pictures. What am I supposed to do? And my answer is, think. In other words, H2O has developed one of the few automated machine learning platforms. We call it driverless AI. It doesn't crash, by the way, which is nice to know. But that goes ahead and generates features, fits models automatically, et cetera, et cetera. And that has raised the expectations of people, customers, clients, whatever, to think, oh, well, it's supposed to do everything, and the answer you get is perfect. Well, I want to show you why, even with as fantastic a program as that is, that's not the answer. Someone showed earlier in a talk this, or maybe it was outside, this cycle, I think I saw it on a t-shirt, a cycle of analytics. And it's a truism in machine learning that, as Kagglers well know, you don't get a final answer. You get a model, you get a fit, and then you look to see what to do next. How do you fix it, and so on. And that's what we're going to take a look at. We're going to look at the kinds of things that AutoViz identified, and that is outliers, distributional anomalies, logical anomalies, model anomalies, feature anomalies, and finally proxy anomalies. So let's first define an anomaly. It's used all over the web. Our program companies say, or people say, finds anomalies in the data. Well, what's an anomaly? An anomaly, I look at it consistent with a Bayesian approach. That is, an anomaly is an observation inconsistent with my personal prior set of beliefs. So if I have a set of beliefs and I suddenly encounter a surprise, that's an anomaly. Now, outliers are a very special kind of anomaly. They only apply to a limited set of data, and that is they are generated by a probabilistic process in a vector space. All outliers are anomalies, but not all anomalies are outliers. Now, a distributional anomaly is a distribution of data that doesn't fit our conventional expectations. In other words, we're going to try to do a histogram and we discover it's highly skewed or it's multimodal or so on. A logical anomaly is something that is completely inconsistent with the axioms of a system that we generated in expectation of getting results from this data set. And I'll show some examples of that. Like a car getting negative miles per gallon, unless you backwards take the odometer and change it. All right, a model anomaly is an observation inconsistent with the model. A feature anomaly, especially for you Kagglers who generate features to add to the set of columns that you use in your model, well, a feature anomaly is a result that's based on a specific set of features. And you put them all together and you get a result of your model that makes no sense to you. Finally, a proxy anomaly involves highly correlated predictors. All right, outlier detection, begin with that. It's got a 200-year history, although you won't generally see that in recent reviews. They'll ignore the fact that anybody before 2010 ever thought of an outlier, but it goes back to astronomers in the 18th century who were very good at measuring astronomical phenomena, but they were very concerned when one of the measurements, say, was way out of the range of what they expected. And they really wrestled with what to do with that one discrepant observation. And that accompanied the early history of statistics, where the normal distribution came to be used in analytics and so on. Now, if you want to learn about outliers, really learn about it, Barnett and Lewis remains the authoritative reference. The other two are interesting approaches to anomaly detection that follow on Barnett and Lewis's result. So I advise you, if you really want to pursue this further, beyond what you see in, say, the computer science publications and reviews on this topic, you go look at Barnett and Lewis. Now, for univariate outliers, we'll cover them first. There are two approaches to identifying them. One is the distance from the center rule, which is what the astronomers were worried about. And that is what it says. That red dot is far from the center of mass of all those other dots, and we call it an outlier. The one on the right is a plot that many of you have seen. It's called a box plot. It was invented by the statistician John Tukey. And box plots will show those red dots as outliers. Tukey called them outliers. This is not an outlier identification method. So if you read most blogs on the web involving visualization, they will say, oh, start with a box plot. And the answer is, no, don't. Or, yes, start with a box plot, but don't think those things are outliers because there's no n in the formula that Tukey used to compute those values. And so if n were very large and I had lots of dots, you're going to see many, many outliers, which are not really outliers. All right. The gaps rule is the second major way of thinking about them, and that is any point that is far from its nearest neighbor. And that means that algorithm will capture inliers as well as outliers. Now, these generalize beautifully to higher dimensions. The distance from the center rule states that the red dot is far from the density, that's a joint bivariate Gaussian or bivariate normal density, and the red spot is quite far from the center of that ellipse, and we call it an outlier. Now, the theory behind that involves using things like Mahalanobis distances, which adjusts for covariances among the variables and so on, but the point remains. That's basically what the concept is. Now, the gaps rule generalizes beautifully too. You have to compute k nearest neighbors, or the nearest neighbor, for each of those points in order to identify them. Now, just quickly point out that a lot of visualization people, especially bloggers, think that we can use visualizations to find outliers. Trust me, you can't. Here's an example on the left. Those 2 points, when computed with the appropriate test, because I generated a bivariate normal distribution, those 2 points are outliers by using Mahalanobis's chi-square test. However, if you take the right point in that left plot, project it over to the margin there, it's in the middle of the histogram. So the marginal histogram is going to conceal the fact that it was an outlier. The same with the other histogram, it's in the middle of that. So the only way to compute that is to do it in 2 dimensions, statistically, and then you can color those red points. Problem is, what about 3 or 4 or 5 dimensions? Well, you have to compute that distance in the higher dimensions. Let's not waste too much time on the right-hand plot, except to say that's a generalization to 3 dimensions, and that red spot is an outlier But in all three marginal bivariate distributions, it's inside that ellipse, so you wouldn't think it's an outlier. Now, I showed you parallel coordinates. Very popular display among people who do visualization. If you know what you're doing, it's a great display, but you can't use it to find outliers. For this data set, which is actually the adult data set from UC Irvine, it's from census data in the US. Those 2 points, they're actually a dual of points, mapped to each of those variables, so they're mapped as profiles. Those are both outliers. But look at the one where the weight is small. Follow that curve, that profile, and you'll see it's in the middle. So again, as in the earlier example, the parallel coordinates are going to conceal the outliers. They're not going to show them in many, many cases. Now, the other problem with outlier detection is if it's not based on probability theory, it's of no use to you, I would claim. On the left is an example on the web that was used to illustrate how good the local outlier factor test is. That's LOF. And it's an ingenious, actually, nearest neighbor, it's k-nearest neighbor type of algorithm. The only problem it doesn't give you any probabilities. So you look at those points, and the person on the blog said, oh, it found all those outliers. But they're not outliers. The plot on the right is the same data set, and a good outlier detection algorithm would not have found any outliers. Often in statistics, it's every bit as important not to find a result as it is to find a result. You certainly know this when you do classification, that false positives and false negatives are very important when you go and look at the overall behavior of a confusion matrix. All right. Again, probabilities. If the algorithm does not issue probabilities, then how would we find this result? These are 4 outliers in a time series data set consisting of the US unemployment rate. That happened, as I think you know, after the collapse of the mortgage markets in the US, where many basically false instruments were sold to people, and they got a big haircut. So how many years after that happened were they outliers? How long did it take for the economy to recover? Well, the outlier algorithm that was applied here in multivariate space says there were 4 years. Without that, a specific probability associated with them, there would be no way of knowing. Now, outliers can bias predictions. We all know that. But I'm going to show you how harmful they actually can be. Here are 3 variables, all of which are standard normal variables. And I generated them and fit a plane using ordinary least squares. That plane is basically flat. And I took driverless AI from H2O and fit a model, and it came up with nothing except one interesting statistics. The root mean squared error is 1, which is actually what you expect for a standard normal distribution. It's the standard deviation. So I added one more point to this data set. See the point down on the left that's at 0, 0? That's all the data we saw in the previous plot, but I've added one point way up there. So now what happens? Look at the root mean square error. It's ridiculous. It has paid attention to that outlier in the fitting. Now, there are some methods that can deal with this problem, and they're generally involving robust methods. I will say at the outset that deleting outliers before you model is not generally a good idea, unless you know what caused them. A good example that I have in the Grammar of Graphics, my book on visualization, involved an article in the American Sociological Review which found that the average number of times married couples over 50 had intercourse was in the dozens. I think it was like 60 times a month. And it strains credulity, especially if you're over 50. However, the problem was the researcher used a data set in SPSS, and in the old days, missing values were recorded as 999. And the person didn't know that and added the 999s into the computation of the result. So sometimes you know an outlier is impossible, and by all means, you better delete it before you model. Other times, consider using a robust loss function, which are available in machine learning packages right now. Now, one thing I wanted to just cover tree-based methods, because there is a myth going around among some people that because tree-fitting algorithms like AID or random forests or gradient boosting methods on trees are immune to this problem. That's only true if it's outliers among the predictors, because remember, trees split off regions, and those regions are rectangular or hyperrectangles. And so if you have an outlier on one of those predictor variables, the tree's going to split it off and put it as a singleton branch, and we'll trap it that way. But if you have a dependent variable that has outliers, forget it. It's going to be a mess. And that's true. It will be biased. That is true whether you use an ensemble method and add the trees together. You're going to get a biased estimate. So you better worry if you detect outliers on your dependent variable. So there are, again, the workarounds are the same that you would think for regression models. Now let's move on to distributional anomalies. Most classical statistical prediction methods assume a normal distribution. By that I mean that for a model, a regression model, for example, or analysis of variance, the residuals to the model are assumed to be normally distributed. And equivalently, because of another assumption, conditionally normally distributed. That's because for those methods, like t-tests, f-tests, you need that normality assumption to a good extent. I mean, it's more complicated than that when you get into skewness and other violations, but basically that's the idea. In the 20th century, mid to late 20th century, other statistical methods were designed for other distributions. So I'm sure all or most of you have fit a logistic regression to binary response data or multinomial response data, or Poisson regression for count data, negative binomial, and so on, zero inflated. And you're best fitting those models, if they are appropriate, without going ahead and trying what we'll talk about next, which is transformations. A friend of mine, Dan Steinberg, who formed a company called Salford Systems that worked with the inventors of random forests, Leo Breiman, Jerry Friedman, the other groups at Stanford and Berkeley. Dan won one of the earliest contests at KDD before Kaggle existed. And I asked him, how'd you win that model? Well, Dan is an economist, a PhD economist from Harvard. And you know, economists spend all their time learning these esoteric models. And he told me, I saw the data set, I heard the description of the data set, I knew it was a logistic model. So I just used logistic regression. The fact is, I guess you know that if you generate a data set based on, say, a logistic model or even the normal distribution, there's absolutely no machine learning model as an alternative, meaning trees or deep learning or anything, that can do better than logistic regression. That's just axiomatic. By doing better, by the way, I mean in the long run. You've done all your training, testing. I'm talking about when you get to scoring and you look at the long-run process, machine learning models can't beat classic statistical models if the data were generated by the classical statistical process. Now, but sometimes you don't know, well, most of the time you don't know that for a fact. So what you'll often do is transform. And here's an example of a favorite data set on mine, is brain weight and body weight of animals. And it looks pretty extremely skewed on the left. But as we log the brain weight and body weight, we have a beautiful bivariate, probably bivariate normal distribution where regression works really well in predicting the brain weight from the body weight. Now, there's an example of the regression we would do, and we get an R-squared for the raw data of 0.87, and for the log data, 0.92. Tremendous improvement because we transformed. Well, you can do the same thing with tree modeling. Here's an example I computed with a bootstrap tree. I did, I think, 100 bootstrapped trees and then blended them. If you do raw brain weight as the dependent variable, the proportion reduction in error statistic is 0.49. Now, in regression, PRE would be equivalent to R-squared. So on the right, with the logged, it jumps way up to 0.849. So look how transforming a dependent variable, and I think most of you Kagglers know this and have done this in certain instances, it can really help. Now, what we're talking about here is called the Tukey ladder of powers. John Tukey, perhaps the greatest, or I would say one of the three greatest statisticians of the 20th century, devised this formula, x goes to x to the p power. And p determines the degree of shift in the transformation. Now, Box and Cox have a famous formula, they're often cited, that is a slight modification of it that works with, to take, it's based on geometric normal distributions, and basically it's still Tukey's idea, although Box and Cox get the credit. My point is, if you just stick with the simple one that Tukey's talking about, it gives you a class of transformations for positive data, generally non-zero positive data, except for square root, for example. The Yeo-Johnson is available in one of the Python libraries. It's a transformation that applies the Tukey approach when the values are negative. All right, let's get to the anomalies that are logical. And this was a great example I found when I helped a psychologist do a statistical analysis on some survey data. Now, the survey data were computed and served up to the researcher by one of the finest groups in the US. That's the University of Chicago's survey people. But no one noticed this problem. Do you see what's wrong with it? Look at everything above the diagonal. Those are people who report that they've been in their present relationship longer than they've been alive. And actually, maybe there's a possibility there if you allow for transcendental types of theologies. I don't know. But looks to me like a coding error, a reporting error that should have been caught in the coding, and those values should be set to missing. All right, how do you deal? Well, that's obvious. You look for scatter plots like that. You also apply Berkson, who's one of the inventors of logistic regression, way back in the 20s, I think it was, intraocular traumatic test. Does that make any sense to you? He was being joking, of course. You got hit between the eyes with something that was so bizarre, you realize something's wrong here. Now, you can also apply logical filters, but those kinds of things, when you do data prep, wouldn't have caught the age scatter plot. Let's get on to model anomalies. These are the things that appear after you fit a model. And I'm sure many of you have looked at this issue. I want to show you residual plots, which unfortunately do not appear in many publications. If you read what I consider to be the Bible of machine learning, which is Friedman and Hasty, Friedman, and Tibshirani. I'm sure all of you have read that book. You will see some attention given to this issue. Here's 3 fundamentally different models I have fit to the same data set. Linear model is clearly violating, its assumptions are clearly violated. And I'll describe what those assumptions are. They have to do with the fact that there isn't a uniform kind of pattern of those residuals across that red zero regression line. A nonlinear model fit the data a little better, but it still looks pretty, as we say, heteroscedastic, meaning the variance is changing across the zero level. And how many of you compute tree residuals? Do I see any hands? You should. And you should, if you fit ensembles or any kind of tree model, go ahead and plot residuals against estimates. It's so simple. And then you look and you see, gee, that looks a little better. I've got some scatter in different places that's a little worrisome. But instead, what do I see recommended out there on these blogs? And again, I'm only insulting blog writers. Here's a plot that's right there on Stack Overflow that someone says you should do. Plot the actual values against the predicted values. That plot is useless. You have just smeared parts of the model into other parts of the model that are not independent. The whole point of plotting residual against estimate is that they are independent. You've taken the variation out of them. This one is fun because it's also recommended, but someone is asking on Stack Overflow, I got these data and I put them through Excel and I got this black regression line, but the red is obviously a much better fit. Well, this person fundamentally didn't understand the concept of regression. Regression is a conditional prediction method. If X is over here, here's my most likely prediction. If X is over here, here's my most likely prediction. And if you look carefully at the red line, that's not true for those data. Well, someone actually corrected their misconception on that matter. Here is the plot of that smeared one I showed you earlier. That one, here's what you're supposed to do. And actually, the residuals look just fine. They're above and below the line, uniformly across the predicted values. Now, I want to show you, and this might be for the first time, residual plots for some very well-known models. This is the Kaggle data set of Rossmann stores. What we're trying to do is predict sales in these stores. And here we took a generalized linear model, and I've colored them by whether or not the stores were closed or open, because if they're closed, sales have to be 0. Well, uh-oh, they're way below. They've underpredicted the sales, and they're saying they're negative. So that's not such a good model. And the plot looks terrible, right, from everything I showed you earlier. Now we got an improvement. This is a deep learning model. I think it's TensorFlow ran it. But that's not good either. Look, it's got a little tiny straight line down here at the bottom for those more than arguably, certainly 0 sales. So we do another model and we look at the residual plot. This model is a gradient boosted tree. It's an ensemble that has a similar problem. One other problem here is, notice it looks like a funnel off to the right. The variance is getting larger. That's a big problem. So here we got a distributed random forest, and it got the zeros pretty well. There are a few exceptions. I want you to focus on the idea that the variance of those residuals is increasing. This is called heteroscedasticity in the residuals. It's a bad problem. I want to point out that in statistics we know, do not trust a single statistic. There is no number that represents or characterizes a whole distribution. Except in theory, for example, a Poisson distribution has one number, and that's lambda, the one parameter, lambda. But look on the left. The statistician Frank Anscombe at Yale made 4 scatter plots that all have the same correlation. I'm only trying to point out here that the computation of RMSE, which is called normally the standard error of the estimate, normally in statistics, is a simple statistic, but it's not representing what went on in that plot, is it? In other words, I should have known that if I tried to predict a very large number of sales way off at the end there, the error of my prediction is much larger than for stores that have very small sales. And so if you're consulting or contracting to a bank and you're helping them to create a credit score, you need to be aware of that. I don't care how good your RMSE or AUC, for that matter, which is a terrible measure, by the way, for classification. I don't care what that number is. If you've got a problem like the previous one, you're going to mislead your client. So I'm saying, always look at residual plots after fitting a model. Doesn't matter whether it was automatic or manual. What you're looking for is a band of residuals symmetrically distributed around that zero line that is pretty uniform in its spread. If they don't meet it, then there are things you can add to the model to improve your prediction that you may not be aware of. All right, wrapping up here with feature anomalies. These are apparent when you start generating features, which if you want to win Kaggle, you've got to do. There are all sorts of additional columns that are features you thought of that you would add to the data as transformations of others. So here I computed on the famous graph from Les Miserables a centrality measure on every one of those nodes in that graph. And then I just used an outlier detection algorithm and located Valjean. He is definitely an outlier. He's known by more people. Here's another example, though, where the data do not fall into a nice row-column set, but the data are edge lists. And the question is, you've got, I don't know, in some cases, thousands of these graphs, maybe tens of thousands, and you want to know what graphs don't fit in to all the rest of the graphs. In this case, I computed a bunch of things, the graph diameter, centrality measure, etc. And that graph at the bottom, all the rest are trees. The graph at the bottom is definitely not. Here's another feature anomaly based on text analytics. And these were, each of them was a document with thousands of words, many thousands of words. And we embedded them in a multidimensional scaling and then used an algorithm to detect that Ulysses, which very few English speakers have read because it's got so many words that are made up, neologisms, so-called. It's a very difficult book to read. Well, lastly, proxy variables are ones that often get ignored. When we do modeling, we are not aware of them. Carrying a purse is a proxy for gender, except in New York City and maybe Provincetown, or maybe in Moscow, I don't know anymore. But certainly body mass index is a proxy for weight. So these can cause us problems. And basically they bias models. When we end up having two or more highly correlated predictors in a model, even for trees, these can cause you problems. Well, certainly perfectly correlated variables can't even be modeled in regression models unless you use methods like the lasso or stepwise regression, certain approaches. And this is a classic, well-known phenomenon called multicollinearity. But other methods have difficulties. Here's trees. Let's just assume A and B are perfectly correlated. It also works even if they're almost perfectly. A single tree will split A and or B on different branches. You won't know they are correlated, and those trees you might get will predict identically well. So suppose one of them was phases of the moon, and another one was your astrological sign, and you might see them and think, oh, those are important predictors, when in fact they're mirroring each other and are basically worthless in terms of interpreting the result. For random forests, each tree that's generated is independent because of the way it works, but the final result is going to have an unknown blend of A and B, which are presumably pointing to a common underlying variable that you weren't even aware of. Boosting can pretty much help here, but because it will only favor A or B. So when you get a boosted tree, it's going to work pretty well. But the problem is, which one it picked was arbitrary. At least it's not blending them. All right. This is the conclusion. That's what we went over. And I'm going to conclude with a slightly insulting statement, but just say, and if you don't be insulted, don't raise your hand. I'm just saying, if you don't do visualization, get on the train. You need to do it. And this is true whether you care about explainability, like this whole new thing of interpretable models and so on, or whether you don't and you're running a Kaggle competition. And I would bet that almost all of you Kagglers out there actually have done these plots. So if you haven't, do them. Thanks. And thanks to Alex. I think I just used up his entire data plan because he made this possible by tethering this as a hotspot, his phone.
So, any questions to the speaker?
Thank you for your presentation. Considering the H2O.ai service, is it possible, is there a way for you to use it, and what happens to the data set which is uploaded? Could you please explain the term of service or something? I mean, sorry. If I upload the data set, the rights on the data set is preserved, like it's mine, or it's some kind of shared for person usage? Thank you.
Well, I think you've got right into a pretty deep question. To put it personally, I've taught graduate statistics for about 40 years in the university. And until I joined a machine learning company, actually I joined Skytree, which went out of business, and then moved to H2O, I had never seen data sets so weird. If you go to a statistics book, all these examples, height of students, their IQ, everything looks beautifully normal. And many of those data sets were constructed out of IQ tests, or things where they took advantage of the central limit theorem. You know, when you add a bunch of variables together, even if they're not normally distributed, the sum, under certain trivial assumptions, the sum is going to be normally distributed. So my answer to you is, I don't know. You really need, when you look at these weird data sets and see scatter plots or other visualizations that have weird patterns, you really have to think deeply about what could cause those. And I think when Kaglers worry a lot about leakage in models, they're doing exactly that. They're thinking beyond just saying, oh, that variable ought to be in there because it predicts really well. So I hope I understood your question on that point. It requires deep thinking.
Anyone else?
Good morning. Sorry, I'm here. Okay. So, first of all, that can be a little bit insulting, but I think you're expecting too much from our auditory here. And, and the actual question is there any commonly used algorithms for doing heuristics on data sets for searching dependencies?
Well, the most obvious one is to compute all possible correlations. That doesn't take care of strings, however, and so one of the algorithms underlying that network diagram that I showed you in AutoViz involved 3 different kinds of correlations. And if you email me, I can point out what those are, but they're for 2 continuous variables, that's Pearson R squared. For continuous and categorical, you have things that can be point biserial and so on. So that's, I think, one of the best ways. When you compute those things, you can also then do a singular value decomposition and see how many factors emerge. And if there's one huge principal component whose eigenvalue is enormous, you should look at those variables with high loadings on it and say, why are these things so closely related?